So the format for this video is a little bit different because instead of me drawing a lot of stuff for you to see, I have actual models for you guys. We're going to be talking about molecular geometries. There are an almost infinite amount of molecular geometries, but these are very essential for you to memorize if you're going to be studying chemistry or organic chemistry, biochemistry, biology. If you're going to be dealing with biological or chemical systems, it's very important that you memorize what I'm about to show you right now. So the first three aren't exactly geometries, they're functional groups, but we're going to see how it relates to geometry. So let's start off with an alkene. An alkene is a carbon single bonded to other carbons, and we see that this is one of the very important functional groups. And it's a carbon single bonded to multiple other carbons, and it has hydrogen on the carbons. This one is an alkane, and as you can see, it's a double bond between the carbons. So this is carbon, carbon, and the carbons here are attached to hydrogens, and this is a double bond between these two central carbons. Now we get to our first molecular geometry. The functional group alkyne is a triple bond demonstrated through this special model, which I guess they didn't want to make models that had triple bonds because they would be bulky, but in this case they have just like this kind of special blah to symbolize a triple bond between the two carbons. And that's an alkyne. Alkyne has a linear geometry, so that's our first molecular geometry. Also keep in mind that the linear geometry has a bond angle of 180 degrees. Makes sense because it's linear, it's straight. However, if a linear has where it's you can have a linear geometry where you have one carbon here and you have another element here, and then that can create a bent shape. Or you could have another molecule in the middle and another element in the middle that has a greater molecular weight, or it's more electronegative, or the ones on the sides are electronegative, and that can give you a bent shape. So that's our second, a bent shape. Next we have two different forms of trigonal planar. We can have a trigonal bent planar, or we can just have one that's like that. They're actually supposed to be all similar sizes, the bonds, but the model, pushing it inside is a little weird and whatever. So trigonal bent planar and the trigonal planar where it's straight and linear. Now the trigonal planar geometry usually has bond angles of 120 degrees. Now here we have the tetrahedral molecular geometry, where it's kind of like a pyramid. In fact, there's confusion over the difference between this and the pyramidal geometry, which I drew here because it's a little weird with the model, since all of them just kind of it would give us a tetrahedral shape no matter what with the models. The difference is that the tetrahedral has straight up bonds all throughout. So it's the central carbon, and then you have a bond here, a bond out there, and a bond toward us. But with the pyramidal, you just have the carbon or the whatever element, and then you have the bond toward us as demonstrated by this shaded, thick shaded line, the bond to the side with the regular line, and the bond out there with the dashed line. So that's the difference between pyramidal and tetrahedral, which is bonds throughout. It's also important to note that tetrahedral also has bond angles of 109.5 degrees. Next we have Trigonal Bi-Pyramidal, which is, try to imagine tetrahedral, except then you add another bond on the bottom and it sticks out. And because of that and the electronegativity, then instead of them going down like that, they go out to the sides like this. So this is you have kind of like a trigonal planar, mix of trigonal planar and linear, if you can imagine it like that, but it's probably easier to think of it as tetrahedral with an extra bond on the bottom. Next we have square pyramidal, which is kind of like we have 4 bonds here, and then we have the bipyramidal feature. So it kind of gives us a diamond shape in a way, if you can visualize it like that. And we have square planar, which is the 4 bonds. We have a central carbon and 4 bonds around. I didn't make a model because with the models that I have, it's very difficult to make that. So I hope you enjoyed and that you learned a lot about the molecular geometries. Molecular geometries were developed with the VSEPR theory. The VSEPR theory is basically a theory that is used to predict the well, it stands for valence shell electron pair repulsion. That's what the VSEPR stands for, and it's a theory that's used in chemistry to predict the geometries of the molecules and where the electron pairs are, etc. So that's where we get our molecular geometries. Be sure to memorize these and practice drawing them out. That really helps. And if you have models, then do something like this and teach yourself, teach your grandma, teach whoever is interested or not interested. It doesn't matter, but teaching helps to implement it and keep it in your head.